Well, hi everyone, and welcome to our first of three probably videos on energy cycles and the beginning of higher level energetics. So let's get started. So in our studies of thermodynamics, energetics so far, we've largely looked at thermochemistry. So we've looked at exo and endothermic reactions and calculating change in enthalpy using bond enthalpies, Hess's law, and also looking at enthalpy level diagrams. And we're starting to get a much better grasp of what these different terminologies mean. What we're going to do now on higher level is expand on this and start bringing in some thermodynamics as well as thermochemistry. So when we look at thermochemistry, what we're looking at is the idea that thermochemistry is the study of energy transfer between reacting chemicals and their surroundings. So that idea of what's exothermic and endothermic, remembering that exothermic gives energy out in the form of heat into the environment. So energy goes into the environment, causing the temperature of the environment to increase. Whereas endothermic, the energy goes from the environment into the reaction, which means it causes the overall temperature of the environment to decrease because the reaction is absorbing that. Okay, so generally when we do these, we consider work to be done when an object is having energy transferred to it. Okay, so what this means is that when we start to look at how energy is transformed, we start to get into the realm of thermodynamics. So when we look at thermodynamics, we're looking at the study of the relationships between heat, work, and energy. So how do we convert energy into work, and how do we lose it through heat and different things like that? These are typically looked at by the laws of thermodynamics, which usually are studied extensively in physics. But these laws of thermodynamics is where we really start to see physics and chemistry overlap. Okay, so the first law of thermodynamics we've kind of actually already looked at. If you think about, if we look at energy can neither be created or destroyed, it's conserved. This is fundamental to balancing equations, and we see it mostly when we start to talk about the law of conservation of mass. But where we talk about the law of conservation of mass, it's just a little subset of this idea that energy cannot be created or destroyed. It is always conserved. The second law of thermodynamics, okay, is relating to what we call entropy. And you may have heard, if you watch any space documentaries or things like that, the idea that the entropy of the universe is always increasing. We will look at entropy in our next section of this topic. The third law deals with systems approaching absolute zero. Okay, so basically remembering that absolute zero is minus 273 degrees or 0 Kelvin, what this is saying is that all processes cease and the entropy of a system approaches its minimum value of 0 when we are looking at this third law. So as the system approaches absolute zero, all movement ceases and the entropy hits a minimum value. Again, remembering that this is just a theoretical idea. We don't have anything that we've gotten completely to absolute zero yet. But if we did, all movement would stop. Okay, so when we look at these, before we move into our idea of energy cycles and thermodynamics, we need to get a couple of definitions sorted out. So it is important that you know these definitions and know where to find the values and what they correspond to. You'll notice that you have a data book reference here. There is a giant table of thermodynamic data, section 8, and it has a lot of different delta H symbols. So there is one which is the delta H of ionization. So these relate to your first ionization energies, which is exactly the same as what we saw back in atomic structure in SL. Okay, the energy required to remove 1 mole of electrons from 1 mole of gaseous substance to form a positive ion. Okay, so we're removing 1 mole of electrons from 1 mole of substance. Okay, so it's going to be an amount of energy per mole. The atoms have to be in a gaseous state first, otherwise we have to expend energy to get them into the gaseous state. Okay, and in this case, it is important to realize that it is a positive ion that is formed here because we're removing electrons. So this delta HI0, so under standard conditions, the enthalpy of ionization, so we can have any atom in a gaseous state going to a positive ion and releasing an electron. This will correspond to the delta HI0 and will be a positive value because it requires energy. We've got to put energy in, so it's going to be an endothermic process. The opposite of this is when we form negative ions. When we form negative ions, we're not losing electrons, we're not ripping them off, we're actually gaining electrons. And in doing that, we gain stability, which means we go from a higher energy state to a lower energy state. And this will be an exothermic process. So the first on electron affinity is talking about the energy change when 1 mole of gaseous electrons is added to 1 mole of gaseous atoms, forming a negative ion. So an example of this would be chlorine gas, gaining an electron to form the chloride anion. Okay, this is delta H subscript E. Standard conditions is what this little E naught is up here, this little naught here. So we've got chlorine gas plus an electron goes to chloride gas. Again, the delta H for this is a thermochemical equation, so we're going to quote the delta H. It's delta H subscript E is equal to negative 349 kilojoules per mole for 1 mole of substance, and it's an exothermic process because we are forming a more stable ion. Okay, so it's going to have a lower potential energy at the end. So what this means is that we're going to start looking at the enthalpy for lattice formation. Up until this point, when we looked at bond enthalpies, okay, if we looked at bond enthalpies, change in delta H for bond enthalpies, because we're looking at bonds, we've been looking at molecules, covalent molecules. What we're going to look at now is looking at how we work out the enthalpy for the formation of an ionic lattice. Okay, so what we looked at was we looked at the formation of the sodium plus ion and the chloride anion. Okay, this is what has to happen in order for us to form sodium chloride lattice. So we have to have both of these form. So we can look at the energy required to form the positive ion and the energy that is released in the formation of the negative ion, and overall have an enthalpy that would be an endothermic process. Okay, so we can start to add these enthalpies in because this is the energy that is required for the ionization of sodium and the energy that is given off from the ionization due to electron affinity of chloride. But we know that sodium chloride is a solid, so it's highly ordered, it's very stable, so it's actually what we refer to as more energetically favorable than, so therefore the attraction between the two ions is very great. Okay, so what we actually see with the formation going from Na plus to Cl minus, when the attraction comes and we form the stable solid, this is a very exothermic process. Okay, so we get a lot of energy given off when we form the solid. Okay, so what we can see is that we have this formation of the ions, and then the ions coming together and forming the lattice gives off more energy. Overall, we're going to have an exothermic process. To be able to understand this, we need to do basically like a Haber process. Well, Hess's law with the cycle. Remembering that Hess's law said it didn't matter how we get there, we follow the cycle and the change in enthalpy will be the same. When we do this, to determine lattice enthalpy, we draw what we call Born-Haber cycles because we need to look at the different ionizations and then back to the stability. So let's get started with that. So we need to remember a couple of things about ionic lattices. Remembering that they have a crystalline, repeated structure, arrangement of positive and negative ions that alternate. They have strong electrostatic attraction between positive and negative ions. Okay, the stronger the attraction, the stronger the lattice in this case. They have very high melting points because of the strength of this attraction. And the stability of ionic compounds depends on the interactions between the cations and the anions, okay? And they have different arrangements and structures. When we add now this idea of lattice enthalpy, basically what we're saying is that this is a quantitative measure of its stability. The higher the lattice enthalpy, the higher the attraction between the ions. So the stronger the lattice will be. So if we have a high lattice enthalpy, we have a very strong crystalline substance. Okay, so let's look at a few more things in terms of lattice enthalpy. You will notice that we said it was a quantitative measure of the strength of a lattice, which means it's basically a measure of the stability of an ionic solid. The definition that we need to know and get into our notes is that the definition is it is the energy required to completely separate 1 mole of a solid ionic compound into its gaseous ions. So from this point, we are looking at how much energy it takes to separate the ions and turn them into a gas. So we're going from a very stable solid into gaseous ions. So this is going to be an endothermic process, okay? All lattice enthalpies for the IB are endothermic, okay? It's energy taken to disrupt the lattice. Okay, so the higher the amount of energy it takes, the more stable the compound, because it takes more to break it apart. As with all enthalpy values, we can't measure this directly, but we can use calculations indirectly if we assume that the formation happens in a number of steps, and then we can use the data we get from Table 8, Section 8 to work these out. Essentially, it's a Hess's law application to ionic compounds. And then because of that, we need to look at the energies of ionization, electron affinity, so the formation of our positive and negative ions, and as well as the molecular and atomic properties to find the lattice enthalpy, so the formation of a single chlorine atom on its own as well. When we do this and put it into a cycle, it's called a Born-Haber cycle, and this is largely how we will see these questions as we go through and see them in the exams. Okay, so just a note on this. If you are looking at other areas and things like this, essentially lattice enthalpy is the equivalent to bond enthalpies for ionic substances. Okay, remembering that the bond enthalpy indicates the strength of the covalent bond in molecules. Lattice enthalpy indicates the strength of the ionic bond within an ionic lattice. So because of the definition stating that it was the enthalpy change when 1 mole of solid ionic crystal is separated into its component ions in the gaseous state, okay, it means that we need to consider standard temperature and pressure. So these are all done under standard conditions, which we saw by the little naught symbol on the delta H. Okay, and it's going to be an endothermic process. So lattice enthalpy should always end up as a positive value. Okay, so this is defined differently by different people. IB specifically says to go from the solid into the gaseous ions. Okay, so it's going to make it endothermic. Other references that you look at may say it's an exothermic process because they look at the energy to go from the ions to the lattice. It is important when you are doing this that you remember that we are looking at it as an endothermic process as defined by the IB. Overall, the absolute energy change is exactly the same. It's just the sign that changes because it depends on the perspective of which way you're looking at it. Okay, so if you look at the separation of the lattice, we're going into ions. So this will be an endothermic process, and this is the one that the IB wants us to use. Whereas if we look at the formation of the lattice, it's going to be an exothermic process because we're going from a high energy to a low energy. Okay, so that's our definitions. So make sure that at the end of this you are able to define ionization energy, you are able to accurately define electron affinity and draw equations to show those, remembering thermochemical equations, and you get that thermochemical data from your data booklet section 8. Lattice enthalpies are actually given in section 18 of your data booklet. Sometimes you'll have to calculate them. If you are finding something else, you may need to use these. So just remember they're there as well. And in the next video, we will look at how we use Born-Haber cycles to determine the lattice enthalpy. Okay.